Okay, so we have been looking at normal shocks in great detail. We have looked at the shock relations and also on their applications to pitot measurements in supersonic flow, the Rayleigh-Pitot formula, and also the moving shock, how to analyze moving shocks. They can be done by taking properties, writing the equations relative to the shock wave by jumping onto the shock, and then the static variables are related by the same shock equations for the stationary shock. So these are the important concepts. Now let us apply these concepts to some numericals in this class. So the first example, there is a normal shock in a uniform airstream. The properties upstream of the shock wave are V1 is equal to 412 meter per second, P1 is 92 kilopascal, T1 is 300 Kelvin. Determine properties downstream of the shock V2, P2, T2, T02, P02. Also calculate the entropy change across the shock. So how to go ahead with this? We know that shock, the equations for shock are all dependent on the upstream Mach number m1. So if you determine m1, you will be able to get to all other values. But also keep in mind that about the conservation equations, where they can be applied for some quick results. So here if you look at m1, this is v1 by a1, and this is v1 is 412 divided by square root of gamma, that is gamma 1.4 multiplied by 87 multiplied by T1. T1 is 300 Kelvin. This is 1.4, and this turns out to be 1.186. Now you can look at the tables for normal shock. Normal shock tables are exactly similar representation as is for isentropic tables. You have a tabulation of Mach numbers, different Mach numbers, and pressure ratio, temperature ratio, density ratio, downstream Mach number, all of them are given, and also the Rayleigh-Pitot formula or Rayleigh-Pitot is also given. So that is given in the appendices of textbooks. Or the other way is to look at some gas dynamic calculators. They are now very much available. Some of this information was shared to you in earlier classes. So you could use the same things for they have separate modules for normal shocks. So you could use that. From them you can generate the values for the properties. So now what we need to measure is what is P2 by P1. So pressure after the shock, P2 by P1 for Mach number of 1.186 is 1.474. So P2 is nothing but P1 multiplied by 1.474. This is 135.61 kilopascal. Now next we need to determine V2. One way to go about doing this is, of course, you have to go and calculate m2. M2 is known once m1 is known. Another quick way of doing that is using rho 2 by rho 1. You know rho 2 by rho 1, this is 1.3069. In this case V1 is given already. So rho 2 by rho 1 is equal to V1 by V2. So you can use this to get V2. So V2 is 338 sorry, V2 is 315.24 meter per second. Then what about T2? So T2 is do look at T2 by T1, which is 1.1278 for this Mach number, and corresponding to this you can get T2 is T1 multiplied by 1278, and T2 is equal to 338.35 Kelvin. Now what is T02? That is T02 is stagnation temperature. Now is an adiabatic flow, so stagnation temperature will remain constant across the shock. So T02 is equal to T01, and for T01 T1 is given 300 Kelvin, and you know M1. So you know M1. So now here you have to use the isentropic table, so or you have to use the isentropic relations. So be very careful here. 1 plus gamma minus 1 by 2 M1 square. Okay. So you will see that from now on, as we go further into gas dynamics, all these concepts will be used together. You have to apply not only normal shock relations, you will have to apply isentropic relations, and they will come together. Soon we will look at flows through nozzles and diffusers. There it is a variable area duct problem. So you will have a problem associated with variable area ducts, but in them shocks can be present. So do not consider each modules separately. As we go through these modules, all of them are connected to each other. As we go more and more into gas dynamics, all that you had learned earlier will be used ever more. So T01 here will be 384.39 Kelvin. So this remains the same for the shock waves across the shock wave. What about stagnation pressure? Will the stagnation pressure be the same or it is different? You already know there is an entropy change across the shock. So P02 will be less than P01. If you are using tables, P02 by P01 is tabulated. You can readily use the tabulation, or you can also do this by using P02 by P2 is 1 plus gamma minus 1 by 2 M2 square whole power gamma by gamma minus 1. You can use this where you have already calculated V2 across the shock. So you can express M2 as B2 by A2, and M2 is 0.8549. This is readily available. Once you know M1, you can get M2. So all these properties are tabulated, or you can get the relations through online calculators. Directly they will give you P02 by P01, and you can apply that and get to the value of P02, and P02 is 218.6 kilopascal. Okay. So now what is the change in entropy across the shock? That is delta S by R. This is Cp log T2 by T1 as R log P2 by P1. both of these quantities are calculated. So you can calculate delta S, oh not delta S by R, delta S. So delta S is equal to 9.54 kilojoules per, right. um, so now we have solved this problem. Let's go to the second problem. The second problem is that of a re-entry vehicle is at an altitude of 15,000 meters and has a velocity 1850 meter per second. A bow shock envelops the vehicle. Determine the static and stagnation temperature just behind the shock wave on re-entry vehicle center line, where the shock wave may be treated as normal shock. Assume air behaves as a perfect gas with gamma equal to 1.4, R is equal to 287 joules per kg Kelvin. So here we know the altitude, so it is 15 kilometers. You can use a reference atmospheric properties. So P1 static properties will be the same as 1.2108 10 power 4 pascals, and T1 is 216.5 Kelvin. Okay. So this property is known to you. Now a vehicle, re-entry kind of vehicle, you would have come across such shapes. They are usually of a blunted kind, and this bluntness is because of the extreme temperatures that are seen at the nose of such vehicles when they re-enter. So the speed is known, it is nearly it is 1.85 kilometers per second. That means in 1 second it travels 1.85 kilometers, is extremely fast. And when such fast flow impinges on the body, then all the kinetic energy of the gas at the stagnation point can be converted into heat or stagnation temperature, and you can get very high temperature. So the shapes of these bodies are meant to cater to such. So it's a aerodynamic shaping in order to minimize the effects of these very high temperatures, and it's a supersonic flow. So a shock wave develops about this body, and usually over such bodies the shape of the shock is like a bow. It will be of this kind. So that's why it's called a bow shock. We will soon come to the discussions of shocks which are at an angle to the flow, like over here and over here. These are known as oblique shocks. They are oblique all the way, right from all these regions are oblique shocks, but right at the center line, where this bow has this curve, at that particular point if you zoom in, then it is just a normal shock, and this is the body, zoomed up version, and here you have a normal shock. So at stagnation point, or in the region near the stagnation point, properties can be calculated by using the normal shock relations. Flow is subsonic here in this region. So how do we get this now? So you know temperature, so we can calculate the Mach number of the flow. It is 1850 divided by square root of 1.4 into 287 216.5, and the Mach number comes out to be 6.27, quite a good high Mach number. And if you want to calculate the stagnation properties, the stagnation temperature can be calculated directly, because T01 is equal to T02. You just have to calculate T01, which is T1 multiplied by 1 plus gamma minus 1 by 2 m square gamma by gamma minus 1, and you can calculate this T0. You have to put 6.27 here, this is 1.4, and you will get T01 as 1918.74 Kelvin. So that is quite a high temperature, considering that the static temperature is only 216 Kelvin. Now as we are doing stagnation temperature, let us also calculate the stagnation pressure P01. P01 you can calculate, in this case P1 is given to you, so you can calculate P01 using the Rayleigh-Peter formula, which relates P0, we have to calculate P02, that is after the shock. So P02 and P1 is what we have to relate, and that is related by Rayleigh-Peter formula, P1 by P02, and this is 0.0915 for this particular Mach number. So you can get P02 is 6.209 into 10 power 5 pascals. Okay, so this is what you get, and in order to calculate temperature T2, static temperature after the shock, you just need T2 by T1 for a Mach number of 6.27. So you can use that and get to T2. So T2 is equal to 1858.6 Kelvin. So this involved looking at the stagnation region of a body, where the shock can be treated as a normal shock. Now let us do a problem on moving shock wave. So a normal shock moves at a constant speed of 500 meter per second into a still air at 0 degree centigrade and 0.7 atmosphere. Determine static and stagnation conditions present in the air after the passage of the wave. So the wave passes, so it is moving at a speed, W is equal to 500 meter per second, this is the speed, and T1 is given, it is 273 Kelvin, and P1 is given is 0.7 atmospheres. So how to do this problem? It is a moving shock problem. So in order to do a moving shock problem, you have to do the transformation so that you sit on the shock or move relative with the shock, and then it becomes stationary, and so 500 meter per second is imposed in the opposite direction, and here you have a mass motion, so you will get 500 minus up as the speed behind the gas, behind the shock. So now let us see what is the Mach number of this shock. Ms is W by A1, which is 500 by square root of 1.4 287 multiplied by 273 Kelvin. This is 1.51. So this is the Mach number of the shock. Once you know Mach number, you can find out P2 by P1 and T2 by T1. P2 by P1 is 2.493 and T2 by T1 is 1.3269. So rho 2 by rho 1 is 1.8792. So now once you know these ratios, is straightforward to get P2 1.7451 atmospheres and T2 is 362.24 Kelvin. So now what is the velocity of the wave behind the gas? We need to, behind the shock, velocity of the gas behind the shock. We need to know this in order to calculate the stagnation conditions. As we had discussed before, stagnation conditions should be calculated separately. So we can do that by using this condition, W minus UP by W is rho 1 by rho 2. Rho 2 by rho 1 is known, this is 1.879. So 500 minus UP 500 is equal to 1 by 1.879. So UP turns out to be 233.929 meter per second. Now you know T2 is known, so you can calculate what is M2 or M2 after the shock passes over is UP by A2, which is 233.929 divided by square root of into temperature multiplied by temperature, which is 362.24 Kelvin, and this Mach number turns out to be M2 is 0.613, and from the isentropic charts for 0.613 or nearest values to 0.61, you can calculate what is P2 by P02. This is 0.7759 and T2 by T02 is 0.9301. So you get P02 is 2.249 atmospheres and T02 is 389.46 Kelvin. So you get the stagnation properties across the moving shock. So moving shock problem, when one is doing, one has to be really careful that you use the appropriate transformations, look at the frames of references to get the correct answers. These static property relations are the same as that of a normal shock, but stagnation properties have to be calculated in the fixed frame of reference. So we have done 3 problems as examples for normal shocks and moving shocks. From the next class onwards, we will look at unsteady flow problems. The moving shock is a part of it, but there is much more to it. So an example of that is the shock tube itself. So we will look at that in the next class.